These days, if you want your product to be cool, you need to include a few important things when you design it. First, it needs to be intelligent, right? I mean, just about everything we buy these days is smart, from our phones to our refrigerators to our walking sticks. Okay, maybe not that last one. But nobody wants a dumb product anymore, and that means we need some microcontrollers to make our products really smart. We also need to make it green, of course. It needs to barely sip power. Microwatts are way too much. If we want our batteries to last a long time, or tougher yet, if we want to take advantage of the latest energy harvesting technologies, we need to be talking nanowatts. Of course, nanowatts and microcontrollers are two words you normally don't see together, and it makes it challenging to meet both of these requirements at the same time. Hi, I'm Amelia Dalton, host of Chalk Talk. In today's Chalk Talk, we're going to use nanowatts and microcontrollers in the same sentence, over and over. That's why my guest is Jason Tollefson of Microchip Technology. We're going to talk about a radical new line of microcontrollers from Microchip Technology that combine amazing processing capability with almost unbelievably low power consumption. Before we get started, I want to remind everyone that you can click on that Download Now button below your player. There you can download a free white paper that further expands on this topic. Thank you so much for joining me today, Jason.
Yes, thank you, Amelia.
So there has been a big increase in the interest in extremely low power microcontrollers. What do you see as the reason for that increase?
Well, what we've seen is customers asking us for lower and lower power microcontrollers, especially across our 8 and 16-bit microcontroller portfolio. And we see a lot of that demand being generated by the growth in battery applications. Many recent surveys show that there's an increase in the use of batteries for embedded products.
Yeah.
We're seeing interest from customers in energy harvesting. So in order to allow energy harvesting to even be in the application, you need very low microcontroller power.
Absolutely.
We're also seeing governments start to regulate how much power different appliances can consume. There's many regulations going into place around the world, and that's also driving power lower. And we're seeing more rich features integrated into what used to be simple products. So that drives the power consumption up, so you need to balance that with a lower power microcontroller.
Very true. So Microchip has a huge portfolio of microcontrollers. What are the qualifications for one to be extreme low power?
To us, extreme low power really grew out of talking with our customers. And what our customers said is that they really needed their power consumption to be below 1 microamp while they're sleeping.
Okay.
So out of that requirement from our customers, we coined some requirements for XLP, and those are that sleep is 100 nanoamps or less, that if you're running a timer such as a watchdog timer or a real-time clock, that current is under 800 nanoamps. So you can see combining those is under 1 microamp. Now, that was our initial target, and we released many products that met that. But we kept on working at those 3 key parameters because our customers told us those were the things they used the most. So our actual best specifications now, we're down to 9 nanoamps for sleep current. If you're using a watchdog timer, we're 200 nanoamps, and with a real-time clock, we're 400 nanoamps. So we've really driven those numbers down. One thing I want to touch on before we leave this slide is that we started with sleep power. And as we started to get to these low numbers that I just shared with you, we realized that active power is really where we need to go next. So we got to work on that as well. And now we feature microcontrollers with run currents as low as 30 microamps per megahertz.
Wow.
So you've gotten the sleep currents down, now we're getting the active currents down. And along with that, you need to have few resources that are low power as well, and we've done that with our real-time clock, watchdog timer, and a brownout circuit, which is critical in battery applications. You need to know if your battery can still support operations. So those are key things to think about, and that's what we have with XLP.
Great. So can you walk us through the family?
Yeah. So what I'm showing here is a snapshot, which is actually 145 devices in the XLP portfolio to date.
Wow.
So this is just a high-level view At the top are very small 8-bit products. In the middle is our higher-end 8-bit products. And at the bottom are 16-bit products. And the thing to point out here really is we have products from 8 pins all the way up to 100 pins in the family. And from just a few K of flash, for simple applications, all the way up to 128K of flash. So we have a wide variety here. But what you can see from the sleep numbers and from the active current numbers that they're all very low current. And going forward, what I'd like to do, if it's okay with you, Amelia, is to focus on our 16-bit products.
Absolutely.
Okay, so on this slide, we're going to begin with what we call our PIC24 Lite. So this is the very lowest end of our 16-bit products. And we have 10 products in this new family. And the key thing to take away from this is that they're low power, low cost, and low pin count.
Great.
What I'm showing now is an overview of what the products look like.
Okay.
So it's very much a standard 16-bit microcontroller. It has up to 16K of flash. It offers E squared, has an A to D, comparators and communication, several timers, and what you see is low power resources such as an ultra low power wake up, low power brownout, which I mentioned, and a low power watchdog timer. So it's pretty good base set of features and very low current.
So tell us why this is cool. What do we get from using one of these devices?
The slide here shows key features and key benefits.
Okay.
So really, I mentioned it was a sort of a baseline family in the 16-bit. So it's our lowest cost 16-bit microcontroller. So that's one nice thing to know.
Absolutely.
Of course, that reduces your overall cost of the system, as the microcontroller is often, one of your more expensive pieces in that application. The next part talks about our XLP low power mode. So with sleep mode, we're down to 30 nanoamps, and our run mode current is 150 microamps per megahertz, so very low current. This is going to extend your battery life in the applications that we opened with, sort of the medical, metering, those type of things. Anything that has a battery associated with it. We have very small pin count options, a variety of packages in those, starting out at 14 pins and moving up to 28 pins in this family.
Okay.
It has good performance, up to 16 MIPS with our 16-bit core. And it has flexible serial communications. We have what we call our MSSP, which can be configured to be several different types of serial communication, I2C or SPI. And then we have sort of standard PWM and timer capture and compare module. We have a CCP or eCCP. They have different variety of features depending on which one you choose. So those are sort of the standard core of our low-end microcontroller in 16-bit.
Okay, so what if we need more capability than that? Where do we go next?
All right, well, then you'd move up to the PIC24 KA family.
Okay.
So this family moves up in pin count, moves up in memory,
Okay.
and it also moves up in richness of its features.
Great. All right.
So we have 12 products in this family. Looking at the architectural overview, one thing you'll note is our XLP technology. We've taken and added a new module called Deep Sleep that drives our sleep currents down to 20 nanoamps.
Very cool.
And we've also, on this family, we're about 200 microamps per megahertz for run current.
Okay.
Looking at the features, though, this is what I mentioned, that we're adding more richness. So we have now up to 5 16-bit timers. We have up to 3 PWMs with their own associated clock. We have 2 each of serial communications. We have 2 UARTs. So we add a lot more in terms of its capability. And, of course, we go up to 44 pins now.
So what additional capabilities will this give us beyond the basic 16-bit microcontrollers?
One key feature to note is that we now extend the operation range from 1.8 volts up to 5.5 volts. So on the
Okay.
prior family, it maxed out at 3.6 volts.
Ah.
Now we can accommodate a much wider voltage range with this family. And we see customers liking this for really robustness in noisy environments. That's one of the key benefits. Now, we still have XLP technology, as I mentioned on the past slide. But another enhancement is a 12-bit A to D.
Okay.
So we've taken that 10-bit and made it 12-bit on this family. We've also added something called a charge time measurement unit. We refer to it as the CTMU. And this is really a Swiss Army knife of app peripheral for many different applications.
Okay.
It can do things such as implement touch sense for buttons.
Oh,
It can do things such as measuring long periods of time with great precision.
okay.
So if you have, for example, like an ultrasonic sensor of some kind, it's easy to interface to that. So it really has a lot of variety of applications, and we actually have an application note, talks about all the different ways you can use this one module.
Very nice.
Another thing to note is that we've increased the pin count to 44 pins, but we've also brought in very small packages. So we have a 6 by 6 millimeter 48 pin QFN type package for this, so it still fits into a very small footprint.
Very nice. So I want to get started designing with one of these things. What do I need to get started?
I'm glad you asked that, Amelia. We have something called a Microstick for PIC24.
Okay.
And this is a USB-powered debugger and programmer, very inexpensive, and it supports our low-end product family.
Okay.
Now, what's nice about it is all you need is a USB cable. You can plug it in, and you're off debugging and programming.
Nice.
So you can refine your software, get it to the point that you like it, and then it actually plugs into a proto board. We have pins at the bottom, plug right into the proto board. You can now build your application out.
Very cool. So low power design is a complicated problem. You can't just go buy a part and bam, you're done. What do you have that is specific for low power design?
Moving from the Microstick, which is really just an entry-level point,
Yeah.
you'd want to move into what we call our XLP 16-bit development board.
Okay.
So this is a board that was specifically designed for low power. And what I mean by that is we can get to a 20 nanoamp current consumption with this board with software running in it. So that's an important distinction because many boards are not designed that way, and you'll never get to that kind of capability that the micro can provide. So we have a lot of design tricks that we've incorporated into this board
Nice.
that allow you to get there. Also, we have expansion. So let's say you're developing an application, you want to add a radio or some other kind of communication. We can do that because we have a port that is compatible with many of our other pigtails. So
Nice.
those are compatible modules that you can just plug right in and start developing with. This is powered by a variety of sources too. So we can power it from a coin cell, we can power it from AAA batteries, or we can even power it from an energy harvesting kit, which we also offer.
Wow, okay.
So you really can develop a fully featured low power application, try it in the environment that you want to before you commit to actually designing your own custom board.
Fantastic. So I understand you recently introduced a new family to this line. Is that right?
That's right. We've moved well beyond the low end of our products into what we call our PIC24 GA3 family.
Okay.
So this extended our XLP products in 16-bit up to 100 pins and 128K of flash. So really to the higher end of the microcontroller space. And when we did that, we also created some new XLP modes.
Ah, okay.
So we have the standard modes that we talked about, but we added a few more. One is low voltage sleep.
Interesting. Okay.
This is a way to retain the entire state of the microcontroller, but still get great standby current. And on the very next slide, I'm going to show you what that number is.
Very cool. Okay.
And we added the capability to have a battery backup as well. A few other things we did, we enhanced our 12-bit A to D so that we now can have threshold detect.
Oh, okay.
This allows us to run in sleep and actually wait for an event to happen that reaches a certain value. Then we can wake the system up and not waste time going back and forth between run and sleep mode.
Nice.
We mentioned that this really moves us to the top of the 16-bit. What we mean by that is we've added features like LCD. So we now have quite a few segments of LCD that we support. You could see that we've kept the CTMU and moved that forward. We have more comparators, we have more timers, we have more input captures, output compares, PWMs, more serial communications. So just increasing the amount of peripherals that are at your disposal and also putting that into a 100-pin package so that you can actually use all of those great resources.
So you said this was a full-featured device. How does this do with power consumption?
It does very well. What we did is we went to work trying to figure out how to reduce active current even with a big device.
Okay.
And we were able to do that to the effect of actually introducing the lowest current 16-bit device on the market. We got down to 150 microamps per megahertz while running. So that was a really exciting event. Took a lot of design effort, but we got it there. On top of that, we were also able to achieve 10 nanoamps of standby current. We were able to bring forward all of the traits of the best XLP devices that we had in our portfolio to this now fully featured device. So I mentioned that we had this thing called low voltage retention or low voltage sleep. That allows us to retain the entire state of the device for 330 nanoamps.
Okay.
So very low current. Talked about the VBAT battery backup. So we can now maintain our real-time clock regardless of what happens to the power of the application or the system for 400 nanoamps. That's enough to let a coin cell go for well beyond its shelf life of 10 years.
Very true, yeah.
We also added 6 DMA channels. And this is important because we reduce the active current, but we also want to reduce the amount of time you spend running.
Right.
So with a DMA, now you can do 2 things at once. You could be transferring things from memory location to memory location while still using the CPU. Okay. So that's doing more and making best use of your power consumption. And we also added a LCD drive to this.
Okay, that is cool. Tell me more about the LCD support you have.
We added a 60 by 8 common driver. And
Very
what that
cool.
means is you can have up to 480 segments.
Okay.
So what that looks like is what I'm showing here. Now you can have a wide variety of icons. You can have an information banner. So you can actually have text scrolling by here. Where that really becomes interesting is, say, like a thermostat.
Yeah.
We're all moving towards being able to have time of use power delivered to our house. So it may be cheaper one time and more expensive another. Now that information could be displayed on that thermostat. How much am I paying for this energy right now?
Very
so that's
cool.
why having so many segments is important. And it also allows you to tailor the information to the application itself. So you could see here, we have an example of a thermometer or a battery level or be raining. So it just helps you to have more information displayed to the user in a really friendly format for very inexpensive cost.
So what kind of current does this draw?
We also went to work on our LCD driver, and now we've gotten it down to, if you use our internal resistor ladder, just 1 microamp can run a display of this kind.
Wow. All right. Okay, Jason, tell me about the development kits you have.
Well, we introduced a whole new development kit for this family. So it has the LCD glass that I just was talking about with you, has our plug-in module. That's our way of having changeability of different processors.
Yeah.
It's battery powered, and it also supports all of the plug-in modules that we talked about with the XLP 16-bit development board.
Very cool.
So now you can do much the same kind of process. You can develop the code, you can work on how your display will look, you can add RF connectivity, and that's all supported by this development board. One thing I want to mention is that we actually have a battery underneath too. So you can try out that real-time clock battery backup.
Very cool. All right, Jason, I'm totally sold. Where do I go for more information?
All right, Amelia. Well, we're showing the link to the site. It's our XLP landing page.
Okay.
And on that page, you're going to find all the information you need to start your design. So we'll have data sheets there. We'll have ways to find and filter out what products you want. We have videos that tell you and show you the different current consumption of our microcontrollers. We have a getting started page, tells you what tools to buy, where to buy them. We also have application notes that talk about how to use the different features of the products. So really a great place to start, decide what type of application you're after, and then whatever you need to find is there.
Perfect. Well, I think that's all I have time for today. Thank you so much for joining me today, Jason.
Yes, thanks for having me, Amelia. It was a pleasure.
And before we go, don't forget to click that Download Now button below the player to download a free white paper that further expands on this topic. For Chalk Talk, I'm Amelia Dalton. For more Chalk Talks, check out the on-demand section of eejournal.com.